From a dark sky location, far from the interference of city lights, the Milky Way appears as a faint, luminous band stretching across the celestial sphere. Its name, in our language and many others, is derived from this appearance. The Romans called it the Via Lactea, or the Road of Milk, a real stain upon the blackness of night, its true nature a complete mystery. It was a feature of mythology, a river of souls or the path to the heavens, but not an object of scientific inquiry. The first profound shift in our understanding came with the invention of the telescope. In 1610, when Galileo Galilei turned his simple instrument toward that milky band, he discovered it was not a celestial cloud at all. Instead, it resolved into a multitude of individual faint stars, packed so densely together from our vantage point that they appeared to the naked eye as a single continuous smear of light. This was a monumental discovery. The Milky Way was not an atmospheric phenomenon, but a vast collection of distant suns. The universe had suddenly become much, much larger. Yet, even with this knowledge, its structure remained elusive. The prevailing assumption was that our sun was situated at or near the center of this stellar system. In the late 18th century, the astronomer William Herschel and his sister Caroline attempted to map the galaxy through a painstaking process of what he called star gauging. They systematically counted the stars in different regions of the sky, assuming that the brighter stars were closer and the fainter ones farther away. Their resulting map depicted a flattened, irregular disk of stars with the sun positioned near its core. While a revolutionary first attempt, Herschel's model was flawed. He did not account for the presence of interstellar dust, which obscures our view of distant stars, and made it seem as though our solar system was in a special central position simply because we could not see much beyond our local neighborhood. The true decentering of humanity from the galaxy came in the early 20th century with the work of Harlow Shapley. He was studying globular clusters, which are dense, spherical collections of very old stars that mostly exist outside the main plane of the galaxy. By measuring the distances to these clusters, he noticed a curious pattern. They were not distributed evenly around us. Instead, they seemed to be centered on a point far away in the direction of the constellation Sagittarius. Shapley correctly reasoned that these clusters were orbiting the true center of the galaxy, and that our solar system was located far out in its periphery. It was a humbling realization, akin to Copernicus removing the Earth from the center of the solar system. We were not at the heart of our own galaxy, but were instead inhabitants of its distant suburbs. The final piece of the puzzle, defining what the Milky Way truly is, was put in place by Edwin Hubble in the 1920s. By observing what were then called spiral nebulae, he was able to prove that they were not clouds of gas within our own galaxy, but were in fact independent galaxies themselves, island universes of stars lying at immense distances. This discovery defined our home. The Milky Way was not the entire universe. It was just one of countless galaxies, a single magnificent structure in a vast cosmic ocean. Today, we understand the Milky Way to be a barred spiral galaxy. This means it has a central bar-shaped structure composed of stars, from which several spiral arms extend outward. Its main visible component is a flattened disk of stars, gas, and dust, approximately 100,000 light-years in diameter, though only about 1,000 light-years thick. If you were to imagine it as a vinyl record, our solar system would be a single speck of dust about halfway out from the center hole to the edge. We reside within this disk, which is why the galaxy appears as a band across our sky. We are looking at it edge-on, from the inside. This disk is not a uniform structure. It is organized into distinct spiral arms, which are not solid objects, but are instead density waves, much like a traffic jam on a highway. As gas and dust clouds move through these slow-moving waves, they are compressed, triggering intense bursts of star formation. This is why the spiral arms are so bright and prominent. They are filled with young, hot, blue stars that illuminate the surrounding gas. Our solar system is currently located in a minor arm, or spur, known as the Orion Cygnus arm, nestled between two larger arms, the Sagittarius arm and the Perseus arm. At the very heart of the galaxy, concealed from our eyes by thick clouds of gas and dust, lies the galactic center. This is an extreme and dynamic environment. Here, stars are packed together thousands of times more densely than in our own neighborhood. And at the exact center is a source of intense radio waves known as Sagittarius A star. Decades of observation, tracking the orbits of individual stars whipping around this invisible point at incredible speeds, have provided overwhelming evidence that Sagittarius A star is a supermassive black hole. It possesses a mass equivalent to about 4 million suns, all compressed into a region smaller than the orbit of Mercury. This gravitational behemoth is the anchor around which the entire galaxy slowly revolves. Surrounding the central bar and the flat disk is a much larger, more spherical component called the galactic halo. The halo is sparsely populated with very old stars and the ancient globular clusters that Shapley used to find our place in the galaxy. But the visible matter of the halo is only a tiny fraction of its total mass. The vast majority of the Milky Way's mass, perhaps as much as 90%, is in a form that we cannot see and do not understand. We call it dark matter. We know it must be there because of its gravitational effects. The stars in the outer regions of the galaxy are orbiting the center far too quickly. If the only mass present were the stars, gas, and dust that we can see, these outer stars should be flung off into intergalactic space. The gravitational pull of an enormous, invisible halo of dark matter is the best explanation we have for why the galaxy holds itself together. The galaxy is not static. It is in a constant, graceful state of motion. The entire structure is rotating, but not like a solid wheel. The inner parts rotate faster than the outer parts in what is known as differential rotation. Our solar system, at its distance of about 27,000 light-years from the center, completes one full orbit around the galactic core approximately every 230 million years. This journey is sometimes called a galactic year or a cosmic year. Since the Sun formed, it has made this circuit only about 20 times. The last time our solar system was in this part of its orbit, the first dinosaurs were just beginning to appear on Earth. The galaxy itself is also moving through the universe. It is part of a small cluster of galaxies called the Local Group. Within this group, the Milky Way and its largest neighbor, the Andromeda Galaxy, are gravitationally dominant, and we are on a collision course. Andromeda, which is slightly larger than our own galaxy, is hurtling towards us at a speed of about 110 kilometers per second. There is no cause for alarm, as this cosmic event is still about 4.5 billion years in the future. Furthermore, it will not be a collision in the conventional sense. The distances between individual stars are so vast that it is highly unlikely any two stars will actually hit each other. Instead, it will be a gravitational merger. The two galaxies will pass through one another, their structures distorted by immense tidal forces. Over hundreds of millions of years, they will dance together, eventually settling into a single, much larger galaxy, which some astronomers have already nicknamed Milky Way. When we look up at the night sky, we are seeing more than just points of light. We are observing the structure of our own cosmic home. The light from the galactic center in Sagittarius has been traveling for 27,000 years to reach our eyes. The light from the stars on the far side of the disk is an echo from 100,000 years in the past. We are embedded with an immense, rotating system of stars, gas, dust, and a mysterious dark matter scaffolding, all orbiting a supermassive black hole. Our understanding has journeyed from a mythical Milky River to a complex and dynamic island universe, a single entity among billions of others. And yet there is still so much that remains unknown, hidden behind veils of dust or existing in forms that we have yet to comprehend. The Milky Way is also not alone in its immediate vicinity. It is orbited by a host of smaller, satellite galaxies, dwarf collections of stars caught in its gravitational embrace, the most famous of which are the Large and Small Magellanic Clouds, visible only from the southern hemisphere. These companions offer their own clues about how large galaxies like ours are formed and how they grow over cosmic time.
This process of galactic growth is not a gentle one. It is a story of consumption, a form of cosmic cannibalism enacted on gravitational timescales. The Milky Way, with its immense gravitational field, relentlessly pulls on its smaller neighbors. Over millions and billions of years, the tidal forces of our galaxy stretch and distort these dwarf galaxies, stripping away their stars and gas. We can see this process happening right now. The Sagittarius dwarf spheroidal galaxy, for instance, is currently passing through the plane of the Milky Way and is being actively torn apart. Its former stellar inhabitants are being siphoned off, creating vast arcing structures of stars that wrap around our galaxy. These structures are known as stellar streams, and they are the ghostly fossils of past meals. They are incredibly faint and diffuse, visible only through careful, large-scale surveys of the sky that can pick out groups of stars moving together at the same velocity and sharing a similar chemical composition. By mapping these streams, astronomers can reconstruct the accretion history of the Milky Way, tracing the paths of the dwarf galaxies that were absorbed to build our current home. The Sagittarius stream is the most prominent, but dozens of others have been identified, each one a testament to a long-dead galaxy whose journey ended in a merger with our own. This ongoing accretion of smaller systems is a fundamental mechanism by which spiral galaxies like the Milky Way continue to accumulate mass and evolve. The Magellanic Clouds themselves are engaged in this gravitational dance, though their fate is still a subject of some debate. For a long time, they were thought to be lifelong companions, orbiting the Milky Way for billions of years. More recent measurements of their velocity, however, suggest that they may be first-time visitors, just now making their closest approach. If this is the case, their passage is a dramatic event. The gravitational interaction is already pulling a massive ribbon of hydrogen gas from the clouds, a feature known as the Magellanic Stream, which extends over 100 degrees across the sky. In the distant future, whether on this pass or a subsequent one, the Magellanic Clouds will likely be completely disrupted and their contents will be incorporated into the halo and disk of the Milky Way, just like so many dwarf galaxies before them. Beyond the drama of these mergers, the vast spaces between the stars are filled with a substance of profound importance, the interstellar medium. This is the raw material from which new stars are born and the repository for matter expelled by dying ones. It is an extremely diffuse mixture of gas, primarily hydrogen and helium, and a tiny fraction of dust. Though the vacuum of interstellar space is far more empty than any we can create on Earth, this medium is not uniform. It exists in multiple phases, a complex ecosystem of varying temperatures and densities. There are vast, cold, dense regions known as molecular clouds, where temperatures plummet to just a few degrees above absolute zero. It is within the dark, shielded hearts of these clouds that gravity can finally overcome gas pressure, causing clumps of matter to collapse and ignite as new stars. Elsewhere, there is the warm, ionized medium, where gas has been heated to thousands of degrees by the ultraviolet radiation from hot young stars. This phase permeates much of the galactic disk, a tenuous sea of glowing hydrogen. And then there's the hot coronal gas, a bubble of million-degree plasma that has been superheated and blasted outward by the shockwaves of supernova explosions. This intricate multi-phase structure is in constant flux, with gas cycling between the different states, driven by the life and death of stars. The interstellar medium is not merely the empty stage upon which the stellar drama unfolds, it is an active and essential participant. The dust component, though making up only about 1% of the interstellar medium's mass, has an outsized effect on our view of the galaxy. These tiny grains, composed of silicates and carbon compounds, are exceptionally good at absorbing and scattering short-wavelength light, like blue and ultraviolet. This is why distant objects in the galaxy appear redder than they truly are, a phenomenon called interstellar reddening. It is the same basic principle that makes a sunset appear red on Earth, as the light has to travel through more of the atmosphere, which scatters away the blue light. This dust is also what creates the dark lanes and patches we see in the Milky Way, obscuring the light from stars behind them. It was this interstellar extinction that prevented William Herschel from seeing the true shape of the galaxy, and that still prevents us from viewing the galactic center with conventional telescopes. We must instead turn to infrared, radio, and X-ray astronomy to pierce through the dusty veil. This entire system functions as a grand cosmic recycling plant. Stars are born from the interstellar medium, and for most of their lives, they are cosmic furnaces, fusing hydrogen and helium into heavier elements. Carbon, oxygen, silicon, iron, all the elements essential for planets and for life are forged in the cores of stars. When these stars die, they return this newly created material back into the interstellar medium. A smaller star like our Sun will gently puff off its outer layers to form a beautiful planetary nebula, enriching the surrounding space with lighter heavy elements. A massive star will die in a cataclysmic supernova explosion, an event so powerful that it creates the heaviest elements and blasts them across the galaxy at high speed. This enriched gas then cools, mixes with other clouds, and eventually forms a new generation of stars and planets.
This cycle of birth, enrichment, and death has led astronomers to classify stars into different populations based on their chemical composition, which also serves as an indicator of their age. The oldest stars in the galaxy are known as population 2 stars. Found primarily in the halo and in globular clusters, they are metal poor, meaning they have a very low abundance of elements heavier than hydrogen and helium. They are ancient relics from a time before the galaxy had undergone many cycles of stellar recycling. Population 1 stars, by contrast, are metal-rich. Our Sun is a typical population 1 star. They are younger and are found predominantly in the galactic disk, where star formation is an ongoing process. They formed from interstellar gas that had already been seeded with heavy elements by many previous generations of stars.
Logically, there must have been an even earlier generation, the very first stars to form in the universe, which are hypothetically called population 3 stars. These primordial stars would have been forged from only hydrogen and helium, the only elements created in any significant quantity by the Big Bang. Theoretical models suggest that these stars would have been extraordinarily massive, hundreds of times the mass of our Sun. Because of their immense mass, they would have been incredibly hot, bright, and extremely short-lived, burning through their fuel and exploding as supernovae in just a few million years. It was these first explosions that began the process of cosmic chemical enrichment, creating the first heavy elements and paving the way for the population 2 stars that followed. We have not yet directly observed a population 3 star. They are ghosts from the cosmic dawn, but their existence is a necessary step in our understanding of how the universe came to be as it is today. Our galaxy story is still being written. The ongoing accretion of dwarf galaxies, the steady churn of the stellar life cycle, and the slow rotation of the spiral arms are all processes that will continue for billions of years. But the grandest future event on the horizon is the inevitable merger with our neighbor, the Andromeda Galaxy. As they continue their slow, inexorable approach, the two galaxies will begin to feel each other's gravitational pull more strongly. In about 4.5 billion years, they will make their first pass through one another. The vast distances between stars mean that direct collisions will be almost non-existent, but the tidal forces will be immense, flinging long streams of stars and gas out into intergalactic space and completely disrupting the elegant spiral structures of both galaxies.
Over the course of another billion years or so, after several close passes, the two will finally merge and settle into a new, stable configuration. The resulting galaxy, which some have tentatively called Milky Way, will be fundamentally different. It will not be a spiral, but a giant elliptical galaxy, a vast, roundish swarm of stars with little internal structure. The collision will trigger a final, spectacular burst of star formation as the combined gas clouds of both galaxies are compressed, rapidly creating trillions of new stars.
But this starburst will be a final flourish. It will quickly use up most of the available gas, and with the raw material for new stars largely depleted, star formation will then cease almost entirely. The galaxy will become a quiescent, aging system, dominated by older, long-lived red stars. The bright blue lights of the spiral arms will be a distant memory. From there, the future of the galaxy is one of a long, slow, and graceful decline. The era of star formation will be over. The existing stars will continue to shine, but one by one they will exhaust their fuel. The most massive stars will have already gone. Sun-like stars will swell into red giants and fade into white dwarfs over the next few 100 billion years. The last lights to remain will be the dimmest and most frugal of stars, the red dwarfs. They burn their fuel so slowly that they can live for trillions of years, far longer than the current age of the universe. But even they will eventually go out. The galaxy will grow progressively darker and colder, becoming a silent graveyard of stellar remnants, black dwarfs, neutron stars, and black holes, all orbiting a now quiet central supermassive black hole. Over timescales so vast they defy human comprehension, even these remnants may dissolve. If current theories about proton decay are correct, all baryonic matter will eventually evaporate into a faint bath of radiation. The black holes themselves will be the last structures to go, slowly leaking away their mass over googles of years through Hawking radiation. The galactic echoes will finally fade completely, and the structure we call the Milky Way will dissolve back into the quiet, expanding darkness of the universe, leaving behind almost no trace of its once luminous existence. This distant, silent future stands in stark contrast to the galaxy as it exists today, a place of immense activity and structural complexity, particularly at its very core. The galactic center, located some 27,000 light-years away in the direction of the constellation Sagittarius, is a region unlike any other in the Milky Way. It is a place of extremes, where the density of stars is over 1,000,000 times greater than in our own solar neighborhood, and where gravitational forces are dominated by a single, invisible object of incomprehensible mass. Shrouded from our direct view by thick clouds of interstellar dust and gas, this central engine can only be studied with instruments that detect radio waves, infrared light, and X-rays, wavelengths that can penetrate the obscuring veil. At the very heart of this region lies Sagittarius A star, the supermassive black hole around which the entire Milky Way revolves. We cannot see the black hole itself, as its gravity is so strong that not even light can escape its event horizon. Instead, its presence is inferred by its profound effects on its surroundings. For decades, astronomers have meticulously tracked the movements of a small cluster of stars that orbit this central point, known as the S-stars. Their motions are astonishing. One star in particular, named S2, completes a full orbit around Sagittarius A star in just 16 years, a journey that sees it accelerate to over 2% of the speed of light as it whips around its closest point of approach. By applying Kepler's laws of planetary motion to the orbits of these stars, we can calculate the mass of the object they are circling. The result is unambiguous. A compact object with the mass of over 4 million suns must reside within a space smaller than the orbit of our innermost planet, Mercury. The only known object that can contain so much mass in such a small volume is a supermassive black hole. These stellar orbits do more than just prove the black hole's existence. They provide a unique laboratory for testing the laws of physics in an environment of extreme gravity. According to Albert Einstein's theory of general relativity, gravity is not a force, but a curvature of spacetime caused by mass and energy. In the intense gravitational field near Sagittarius A star, the predictions of general relativity diverge slightly from those of classical Newtonian physics. For instance, Einstein's theory predicts that the elliptical orbit of a star like S2 should not be a perfect closed ellipse, but should precess, meaning the point of its closest approach should shift slightly with each orbit. In 2020, observations confirmed this subtle gravitational dance precisely as predicted by general relativity, providing yet another powerful confirmation of Einstein's revolutionary view of the cosmos.
The environment immediately surrounding the black hole is a chaotic swirl of gas and dust. While Sagittarius A star is relatively quiet compared to the supermassive black holes at the centers of more active galaxies, it is not completely dormant. It is constantly accreting a trickle of material from its surroundings, primarily from the powerful stellar winds of nearby massive stars. As this material spirals inward, it is compressed and heated to millions of degrees, causing it to glow faintly in X-rays and emit a persistent flicker of radio waves. This activity is highly variable, with flares occurring when a denser clump of gas is consumed. Astronomers have even observed strange, elongated objects dubbed G-objects, which appear to be gas clouds that are being tidally stretched and pulled apart as they make their perilous journey around the black hole, their substance slowly feeding the central giant.
Moving outward from this central point, we find the galactic bulge, a tightly packed, roughly spherical or peanut-shaped concentration of stars that surrounds the galactic center. The bulge is ancient, composed primarily of older, redder population II stars. It is a dense and chaotic environment, where stellar orbits are not confined to a flat plane like they are in the disk, but are instead highly inclined and randomized, much like the orbits of bees in a swarm. Within this bulge resides another of the Milky Way's major structural components, the galactic bar. For a long time, the central bulge was thought to be a simple spheroid, but more recent infrared surveys, which can peer through the intervening dust, have revealed that it is elongated into a massive bar-like structure, perhaps 27,000 light-years in length. This bar is not a static object, but a dynamic feature that rotates as a solid body. It is composed of billions of stars trapped in elongated orbits that are all aligned in the same direction. The bar's immense gravity has a profound influence on the rest of the galaxy. It acts like a great cosmic funnel, channeling gas and dust from the inner parts of the spiral arms towards the galactic center. This inflow of material is thought to be responsible for fueling bursts of star formation within the central few hundred light-years, and may provide the intermittent fuel source for the central supermassive black hole. The bar is a key driver of the galaxy's secular evolution, the slow, long-term changes that shape its structure and activity without the need for dramatic external events like galaxy mergers.
Beyond the central bar and bulge lies the vast, sprawling disk of the galaxy, the component that contains our own solar system. This disk itself is not a single entity, but is composed of at least two distinct populations of stars. There is the thin disk, a structure only about 1,000 light-years thick, where nearly all of the galaxy's current star formation takes place. It is rich in gas and dust and is populated by younger, metal-rich population 1 stars like our Sun. The spiral arms, the most visually striking features of our galaxy, are located within this thin disk. They are not solid structures, but are instead density waves, areas where the density of stars and gas is slightly higher, causing new star formation to be triggered as the wave passes through. Encasing this is the thick disk, a more diffuse, puffed-up structure about 3,000 light-years thick. It contains an older population of stars, ones that are chemically less enriched and move on more vertically extended orbits. It is thought that the thick disk may have formed early in the galaxy's history, or was perhaps created when a smaller satellite galaxy was absorbed, and its stars were scattered into these puffier orbits.
One of the more curious features of the galactic disk is that it is not perfectly flat. Observations of hydrogen gas and the positions of stars reveal that the outer edges of the disk are significantly warped, like the brim of a tilted hat. The northern side of the disk appears to be bent upwards, while the southern side is bent downwards relative to the central plane. This warp is substantial, with the outermost stars and gas clouds lying several thousand light-years away from the main galactic plane. The cause of this large-scale distortion is still a matter of active research, but the leading hypothesis points to the gravitational influence of our largest satellite galaxies, the Large and Small Magellanic Clouds. As they orbit the Milky Way, their collective gravity exerts a constant torque on the outer disk, pulling and twisting it out of shape. The warp can be thought of as a ripple propagating through the disk as a result of this ongoing gravitational interaction.
Encompassing all of these visible components, from the central black hole to the warped outer disk, is the largest and most mysterious component of all, the dark matter halo. We cannot see it, we cannot touch it, and we do not know what it is made of, yet its existence is undeniable. The primary evidence for this vast, invisible halo comes from the galaxy's rotation curve. If we were to calculate the orbital speed of stars based only on the mass of the stars, gas, and dust that we can see, we would expect stars in the outer regions of the galaxy to move much more slowly than stars closer to the center, just as the outer planets in our solar system orbit the sun more slowly than the inner planets. However, when we actually measure the speeds of these outer stars, we find that they move at a nearly constant high velocity all the way out to the furthest observable reaches of the disk. This discrepancy can only be explained if there is a tremendous amount of unseen mass exerting a gravitational pull, holding these fast-moving stars in their orbits and preventing them from flying off into intergalactic space. This unseen mass is what we call dark matter. It is thought to form a vast spherical halo that extends for hundreds of thousands of light years in all directions, dwarfing the luminous part of the galaxy we can see. This dark matter does not appear to interact with light or any other form of electromagnetic radiation, which is why it is invisible to all of our telescopes. Its presence is felt only through its gravitational influence. The visible Milky Way, with all its stars, gas, and dust, is merely a luminous decoration embedded within this much larger and more massive dark matter structure. It is the dark matter halo that forms the gravitational backbone of the galaxy, the fundamental scaffold upon which all the visible structures were assembled and are currently held together. While this immense dark matter halo provides the gravitational framework, it is not entirely empty of luminous matter. Sprinkled throughout this vast volume is a second, far more tenuous halo composed of stars and ancient star clusters. This is the stellar halo, a ghostly sphere of widely scattered stars that envelops the entire visible galaxy. The stars here are among the oldest in the Milky Way, many having formed over 12 billion years ago. They are typically population 2 stars, which means they are metal poor, having been born from the primordial hydrogen and helium gas that filled the early universe, before successive generations of stars had a chance to enrich the cosmic medium with heavier elements. Unlike the orderly, circular paths of stars in the galactic disk, the inhabitants of the stellar halo follow highly eccentric, randomly oriented orbits, plunging through the disk and soaring high above and below the galactic plane on long, looping journeys that can take hundreds of millions of years to complete. The stellar halo is incredibly sparse. If you were on a planet orbiting a halo star, the night sky would appear profoundly dark, with only a handful of stars visible to the naked eye, a stark contrast to the dense, star-filled skies seen from within the disk. The most spectacular residents of this stellar halo are the globular clusters. These are ancient, gravitationally bound spheres, each containing from tens of thousands to over 1 million old stars packed into a region only a few dozen light-years across. Around 150 globular clusters are known to orbit the Milky Way, acting as luminous fossils from the epoch of galaxy formation. Their stars all formed at roughly the same time from the same cloud of gas, making them perfect laboratories for studying stellar evolution. Gazing into the core of a globular cluster, like Omega Centauri or 47 Tucanae, would reveal a sky ablaze with the light of ancient reddish stars, so densely crowded that they would outshine the full moon. These clusters are relics of the building blocks from which the Milky Way was assembled, the surviving cores of smaller protogalactic fragments that were absorbed long ago. The existence of the stellar halo and its globular clusters is a key piece of evidence for the modern understanding of how large galaxies grow, a process known as hierarchical formation. This model suggests that massive galaxies like the Milky Way were not born in a single monolithic collapse, but were built up over cosmic time through the continuous merging and accretion of smaller dwarf galaxies.
As these smaller galaxies are captured by the Milky Way's immense gravity, they are subjected to powerful tidal forces. These forces stretch and pull the smaller galaxy apart, stripping its stars away and dispersing them into long, flowing ribbons that follow the path of the original orbit. Over billions of years, these ribbons, known as stellar streams, phase mix and diffuse, their stars eventually becoming part of the smoothly distributed stellar halo. Our galaxy is surrounded by a complex network of these streams, each a ghostly remnant of a past meal.
The most prominent of these is the Sagittarius stream, an enormous looping river of stars that wraps around the Milky Way at least once. This stream is the debris trail of the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy that is currently in the process of being torn apart as it passes through the Milky Way's disk. By mapping the positions and velocities of stars within this and other streams, astronomers can reconstruct the accretion history of our galaxy, identifying the victims of its gravitational dominance. Furthermore, the precise paths of these stellar streams are extremely sensitive to the distribution of mass in the galaxy, providing one of the most effective ways to map the shape and extent of the invisible dark matter halo that governs their motion.
The space between all these stars and structures is not truly empty, but is filled with the interstellar medium, a diffuse mixture of gas and dust from which new stars are born, and into which old stars expel their substance when they die. Though its average density is less than that of the best vacuums created in laboratories on Earth, this medium is the lifeblood of the galaxy, the reservoir of raw material for all future generations of stars and planets. Roughly 99% of its mass is in the form of gas, primarily hydrogen and helium, while the remaining 1% consists of tiny solid particles of silicates and carbon compounds that we call interstellar dust. It is this dust, concentrated within the galactic plane, that obscures our view of the galactic center in visible light, absorbing and scattering starlight, and forcing us to rely on other wavelengths to see through the veil.
This interstellar medium is not uniform, but exists in a complex, multi-phase state, with vast regions of dramatically different temperatures and densities existing side by side. In the coldest, densest regions, the gas clumps together to form giant molecular clouds. Here, with temperatures only a few tens of degrees above absolute zero, hydrogen atoms pair up to form hydrogen molecules, and the cloud becomes opaque and dark. It is within the sheltered, frigid cores of these clouds that gravity can finally overcome the internal pressure of the gas, triggering the collapse of fragments to form protostars and eventually new star systems. The Orion Nebula is a famous nearby example of such a stellar nursery, where the brilliant light of newly formed massive stars is ionizing the surrounding gas, causing it to glow vividly.
When massive stars are born, their intense ultraviolet radiation and powerful stellar winds heat the gas around them, creating vast, glowing bubbles of ionized hydrogen known as H2 regions. This warm, ionized medium has a temperature of around 10,000 degrees Kelvin and contributes to the overall pressure balance of the interstellar medium. The cycle of galactic matter continues when these same massive stars reach the end of their short lives. They explode as supernovae, cataclysmic events that blast shockwaves through the surrounding medium. These supernova remnants sweep up, compress, and heat the interstellar gas to millions of degrees, creating a hot, tenuous coronal gas that fills a significant fraction of the galactic volume. At the same time, the explosion seeds the surrounding space with a rich assortment of heavy elements, from oxygen and carbon to silicon and iron, that were forged in the heart of the dying star. This process of chemical enrichment is fundamental to cosmic evolution. Each generation of stars enriches the interstellar medium with more of these metals, providing the raw materials necessary for the formation of rocky planets and, ultimately, life.
Our own Sun is a product of this long history of galactic recycling. It is a population 1 star, relatively rich in heavy elements, indicating that it formed from gas that had been enriched by many previous generations of stars. It currently resides within the thin disk, moving on a nearly circular orbit around the galactic center.
that takes roughly 230 million years to complete. Our immediate stellar neighborhood is also a reflection of the varied nature of the interstellar medium. The solar system is presently moving through a region of unusually low-density, high-temperature gas known as the local bubble. This bubble, stretching some 300 light-years across, is thought to have been carved out by a series of supernova explosions that occurred between 10 and 20 million years ago. We are fortunate to be in such a cleared-out region, as it provides us with a relatively unobstructed view of nearby stars. This quiet journey through a relatively placid region of interstellar space offers a temporary reprieve from the more dynamic and violent processes that continue to shape the galaxy on grander scales.
Yet this local tranquility is not representative of the galactic disk as a whole, for this vast, spinning plane of stars and gas is dominated by a grand and graceful spiral pattern. These spiral arms are the most visually striking features of galaxies like our own, luminous arcs of concentrated light and star-forming activity that wind their way out from the galactic center. From our vantage point within the disk, we cannot see this majestic structure in its entirety, but through decades of painstaking observation across the electromagnetic spectrum, we have pieced together a map of our home galaxy. We now understand that the Milky Way is a barred spiral galaxy, featuring a dense, elongated bar of stars at its heart, from which two major spiral arms and several lesser arms emerge and wrap around the core. These arms are not solid, cohesive structures, but rather intricate patterns of enhanced density, moving through the disk like ripples on the surface of a pond.
The prevailing explanation for their long-lived nature is the density wave theory. This model proposes that the spiral arms are standing waves of compression that slowly sweep through the galactic disk. Much like a traffic jam on a motorway, the pattern itself moves at a constant, slow speed, while the individual cars, representing stars and clouds of interstellar gas, move through it at their own, much faster orbital velocities. As a gas cloud enters a spiral arm from behind, it encounters this region of higher density and gravitational pull. It is squeezed and compressed, slowing down temporarily as it moves through the arm, much as cars bunch up in a traffic jam. After passing through the arm's crest, the gas cloud emerges into the lower density interarm region, where it speeds up again on its orbit. The stars themselves are also affected, their orbits slightly perturbed as they pass through the arm, causing them to linger there for a short time. But it is the dramatic effect on the interstellar gas that makes the arms so prominent. This process of compression within the spiral arms is the primary engine of large-scale star formation in the galaxy. As the giant molecular clouds are squeezed by the passing density wave, localized regions within them are pushed beyond their critical density and begin to collapse under their own gravity, fragmenting into the seeds of new stars. Consequently, where the intense radiation from newborn massive stars ionizes the surrounding hydrogen gas, brilliant clusters of young, hot, blue O and B-type stars, which are so luminous they can be seen from across the galaxy, and the dark, obscuring dust lanes that often trace the leading edge of the arm, where the gas is at its densest just before it ignites. Because these massive blue stars have very short lifespans, often only a few million years, they do not have time to travel far from their birthplace. They live and die entirely within the spiral arm in which they formed, acting as luminous beacons that precisely trace the spiral pattern. The interarm regions, by contrast, are relatively placid and dim, populated mainly by older, longer-lived, and fainter stars like our Sun, which have had ample time to drift out of their natal arms.
Mapping these arms from our position inside the galaxy is a formidable challenge, akin to trying to map a forest while standing in the middle of it, with trees obscuring the view in every direction. In the galaxy, the trees are the vast clouds of interstellar dust concentrated in the galactic plane, which block visible light from traveling more than a few thousand light-years. To peer through this veil, astronomers rely on radio and infrared astronomy. Radio telescopes can detect the specific wavelength of radiation emitted by neutral hydrogen atoms, the most abundant element in the galaxy. By mapping the distribution and velocity of this hydrogen gas, we can trace the large-scale structures it forms. Similarly, observations of carbon monoxide molecules allow us to pinpoint the locations of the dense molecular clouds where stars are born.
Combining these maps with distance measurements to young star clusters and H2 regions, astronomers have identified several major structural components. The two primary arms appear to be the Scutum Centaurus arm and the Perseus arm. Our own solar system is not located in one of these major arms, but rather in a smaller partial arm segment known as the Orion Cygnus arm, or simply the Orion spur, which lies between the larger Sagittarius and Perseus arms.
Moving inward from our local spur, the structure of the galaxy becomes even more complex and dynamic. At the very heart of the Milky Way lies a vast, elongated structure known as the galactic bar. This is a massive, roughly rectangular concentration of stars, spanning some 27,000 light-years end to end. Unlike the spiral arms, which are populated by young blue stars, the bar is composed predominantly of older, redder stars, suggesting it formed long ago and has been a stable feature of our galaxy for billions of years. From our perspective, the bar is oriented at an angle of about 45 degrees to the line connecting the Sun and the galactic center. Its presence fundamentally changes the gravitational landscape of the inner galaxy, profoundly influencing the orbits of both stars and gas. It rotates as a solid body, a giant cosmic paddle that sweeps through the center, stirring the galactic contents.
This immense, rotating bar is not merely a passive collection of old stars, it is a critical driver of galactic evolution. Its powerful and non-symmetrical gravitational field exerts strong torques on the gas in the inner disk. This has the effect of disrupting the stable, circular orbits the gas would otherwise follow, forcing it to lose angular momentum and spiral inward towards the galactic nucleus. The bar acts as a giant funnel, efficiently channeling a steady stream of material from the main disk into the central few thousand light-years. This inflow of gas fuels a prodigious rate of star formation in a region known as the central molecular zone, a dense ring of molecular clouds encircling the galactic core. The bar is therefore responsible for the high concentration of activity and luminosity that characterizes the galaxy's center, a process that continues to build up the central stellar bulge over cosmic timescales. At the very center of this complex hub of activity, at the gravitational heart of the entire Milky Way, lies a truly extraordinary object, a supermassive black hole named Sagittarius A star. Though it cannot be seen directly, as its gravity is so strong that not even light can escape, its presence has been inferred with unshakable certainty. The most compelling evidence comes from tracking the motions of individual stars that orbit this unseen central point. For over 2 decades, astronomers have used powerful infrared telescopes to pierce through the obscuring dust and monitor a small cluster of stars swarming around the exact galactic center. One star in particular, named S2, has been observed to complete a full elliptical orbit in just 16 years. It travels at astonishing speeds, at times reaching over 7,000 kilometers per second, or about 2.5% of the speed of light, as it whips around its closest point to the black hole.
By applying Kepler's laws of planetary motion to the precise orbit of S2 and other nearby stars, astronomers have been able to calculate the mass of the central object they are orbiting. The result is unambiguous. There are approximately 4.3 million times the mass of our Sun, all contained within a volume smaller than the orbit of Mercury. There is no known astrophysical object other than a supermassive black hole that could contain so much mass in such a small space. While currently in a relatively quiet phase, Sagittarius A star is not entirely dormant. It is surrounded by an accretion disk of hot gas that is slowly spiraling into it. Friction within this disk heats the gas to millions of degrees, causing it to emit X-rays. Astronomers also observe occasional, powerful flares of radiation from the immediate vicinity of the black hole, likely caused by the disruption and consumption of unlucky gas clouds or asteroids that venture too close. This slumbering giant is the anchor around which our entire galaxy revolves.
Stepping back from the intricacies of the central engine and the spiral arms allows us to contemplate the motion of the galaxy as a whole. When we measure the orbital speeds of stars and gas clouds at different distances from the galactic center, we find something deeply puzzling. Based on the distribution of visible matter, like stars and gas, which is heavily concentrated towards the center, we would expect orbital speeds to decrease with increasing distance, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. This is what Newtonian gravity predicts. However, observations of the Milky Way, first pioneered by the astronomer Vera Rubin for other spiral galaxies, show a completely different reality. The galactic rotation curve does not fall off as expected. Instead, once you move out beyond the central bulge, the orbital speeds of stars remain remarkably constant, or even slightly increase, all the way to the farthest observable reaches of the galactic disk.
This flat rotation curve presents a profound discrepancy. Stars in the outer galaxy are moving far too quickly. According to our understanding of gravity, the visible matter in the galaxy simply does not provide enough gravitational pull to hold these fast-moving stars in their orbits. They should have flown off into intergalactic space long ago. The inescapable conclusion is that the vast majority of the mass in our galaxy is not in the form of stars, gas, or dust. It must be something else, something that does not emit or interact with light, something we have come to call dark matter. The observed rotation curve can only be explained if the visible disk of the Milky Way is embedded within a truly immense, roughly spherical halo of this mysterious, invisible substance. This dark matter halo extends hundreds of thousands of light-years in all directions, far beyond the most distant stars and globular clusters, and its total mass is estimated to be at least 10 times greater than all the luminous matter combined. It is this unseen halo that provides the dominant gravitational force governing the galaxy's structure and rotation, a silent, invisible scaffold upon which the brilliant visible components of the Milky Way are built.
The nature of this dark matter remains one of the most profound and persistent mysteries in all of science. Decades of searching have yet to reveal its true identity, but theoretical physicists have proposed several intriguing candidates. The leading hypothesis for many years has been the existence of weakly interacting massive particles, or WIMPs. These are hypothetical, heavy, slow-moving particles that, as their name suggests, would interact with normal matter only through the weak nuclear force and gravity. They would be entirely invisible to us, passing through the Earth and our bodies by the billions every second without a trace. Yet their collective mass on a galactic scale would provide the missing gravitational glue. Enormous and highly sensitive detectors have been built deep underground, shielded from cosmic rays, in an attempt to catch the vanishingly rare signal of a WIMP colliding with an atomic nucleus. But so far, these searches have come up empty. Other candidates, such as the much lighter axion or even primordial black holes formed in the earliest moments of the universe, are also being actively investigated. The evidence for dark matter's existence is not limited to rotation curves alone. It is also seen in the way its gravity bends the light from distant galaxies, a phenomenon known as gravitational lensing, and in the large-scale structure of the universe itself, which could not have formed the cosmic web of galaxies we see today without the gravitational influence of this unseen component.
The Milky Way, with its vast dark matter halo, does not exist in isolation. It is one of the two largest members of a small, gravitationally bound collection of galaxies known as the Local Group. This cosmic neighborhood spans roughly 10 million light-years in diameter and contains more than 80 known galaxies, though most of these are faint, small dwarf galaxies. Our largest and nearest major galactic neighbor is the Andromeda Galaxy, also catalogued as Messier 31. Located about 2.5 million light-years away, it is faintly visible to the naked eye as a small, fuzzy patch of light in the autumn sky of the northern hemisphere. Andromeda is slightly larger and more massive than the Milky Way, containing perhaps 1 trillion stars compared to our own galaxy's few hundred billion, and it serves as a near-perfect sibling for comparative study. The third largest member of the Local Group is the Triangulum Galaxy, or Messier 33, a beautiful but more loosely wound spiral about half the size of the Milky Way. The rest of the group consists of a swarm of satellite galaxies, diminutive collections of stars that orbit the larger galaxies like moths around a flame.
Our own Milky Way is attended by a retinue of these smaller companions. The most famous and prominent are the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible only from the southern hemisphere. For millennia, they have appeared as detached fragments of the Milky Way, permanent, ghostly clouds in the night sky. We now understand them to be on a very long, looping orbit around our galaxy, currently making one of their closest passes. Their gravitational interaction with the Milky Way is a dynamic and dramatic affair. The immense tidal forces of our galaxy are pulling long streams of hydrogen gas from the Magellanic Clouds, creating a vast structure known as the Magellanic Stream that wraps a significant portion of the way around the sky. In turn, the gravity of the clouds has likely perturbed the outer disk of the Milky Way, contributing to the gentle warp seen in its hydrogen gas layer. These interactions are a prelude to their ultimate fate. Over the next few billion years, their orbits will decay and they will be completely torn apart and absorbed, their stars and gas assimilated into the body of the Milky Way.
This process of galactic cannibalism is a fundamental aspect of galaxy evolution. The Milky Way we see today was not born in its current form, but has been built up over cosmic history through the steady accretion of countless smaller dwarf galaxies. Evidence for this violent past is written in the motions and positions of stars in the galactic halo. As a dwarf galaxy is captured and tidally disrupted, its stars are not scattered randomly but are stretched out into long, coherent ribbons or streams that continue to orbit within the larger galaxy's halo for billions of years. By carefully measuring the positions, velocities, and chemical compositions of millions of stars, astronomers have been able to identify numerous such stellar streams crisscrossing our galactic halo, each one the ghostly remnant of a long-dead galaxy. One of the most significant of these is the Sagittarius stream, the remains of a dwarf galaxy that is currently in the process of being shredded as it passes through the Milky Way's disk. These discoveries paint our galaxy as a living, growing system, constantly feeding on its smaller neighbors to build up its size and mass, a history of cosmic mergers etched into the starry skies.
This history of growth by merger is far from over. In fact, our galaxy is on a collision course with its largest neighbor, the Andromeda Galaxy. By measuring the slight blue shift in Andromeda's light, we know that it is hurtling towards the Milky Way at a speed of approximately 110 kilometers per second. While their vast dark matter halos may already be starting to interact, the main galactic disks will not begin to merge for another 4.5 billion years. This future event will not be a cataclysmic crash in the way we might imagine. The distances between individual stars are so immense that direct stellar collisions will be exceptionally rare. Instead, it will be a slow, stately, and majestic gravitational dance played out over hundreds of millions of years. As the two galaxies pass through each other, their spiral structures will be utterly destroyed by the immense tidal forces. Great tendrils of stars and gas will be flung far out into space, creating spectacular tidal tails. The galaxies will then pull back together for a second and then a third pass, the cores oscillating around each other as they slowly lose orbital energy and sink together.
During this protracted merger, the vast reservoirs of interstellar gas from both galaxies will be compressed and funneled toward the center of the newly combined system. This will trigger a spectacular burst of star formation, a galaxy-wide firestorm that will forge hundreds of millions of new stars, lighting up the cosmos with a brilliance our galaxy has not seen since its youth. After this starburst phase subsides, the combined system will eventually settle down into a new, stable configuration. The beautiful, delicate spiral patterns will be gone forever, replaced by a single, giant, and relatively featureless elliptical galaxy. Some astronomers have playfully nicknamed this future galactic home Milkomeda. The supermassive black holes at the centers of each galaxy will also eventually find each other, spiraling inward and merging to form an even larger black hole at the heart of the new elliptical giant. From the perspective of a future Earth, assuming it survives the Sun's own evolution into a red giant, the night sky would transform over millions of years, with Andromeda growing ever larger until it filled a significant portion of the view, its structure distorted as the merger unfolds, creating a celestial spectacle of unimaginable grandeur.
Looking even further into the cosmic future, the fate of our merged galaxy, and indeed all galaxies, is one of slow, inexorable fading. The great starburst triggered by the merger will be the galaxy's last grand creative act. It will consume a significant fraction of the available interstellar gas, and with no new gas flowing in from intergalactic space, the fuel for creating new stars will be exhausted. Star formation will slow to a trickle and eventually cease altogether. The brilliant, massive blue stars will be the first to go, their short lives ending in spectacular supernova explosions. Over trillions of years, the longer-lived sun-like stars will one by one exhaust their nuclear fuel, puff off their outer layers as planetary nebulae, and fade into the quiet oblivion of white dwarfs. The galaxy will grow progressively dimmer and redder, its light dominated by the faint, ruddy glow of the longest-lived and least massive stars, the red dwarfs. These incredibly frugal stars can burn for trillions of years, far longer than the current age of the universe, and will be the last beacons of starlight in a darkening cosmos.
Eventually, even the red dwarfs will burn out, leaving behind a galaxy of cold, dead stellar remnants, black dwarfs, neutron stars, and stellar mass black holes, all orbiting the central supermassive black hole in profound darkness. Over imaginable timescales, far beyond anything we can truly comprehend, these remnants will themselves decay or be consumed. The orbits of the stellar corpses will slowly decay due to the emission of gravitational waves, causing them to spiral into the central black hole. On timescales so vast they defy description, even the black holes themselves are predicted to evaporate through a process known as Hawking radiation. One by one, the last vestiges of structure and matter will dissolve back into a faint bath of low-energy particles. The great, luminous age of the universe, the stellariferous era in which we are so fortunate to live, will be over. The echoes of the Big Bang, which once rang out in the form of brilliant galaxies and the light of a trillion stars, will have finally faded into a cold, dark, and silent equilibrium. Our cosmic home, born of fire and gravity, built over eons through the quiet dance of stars and the patient assembly of smaller worlds, will dissolve back into the endless, quiet expanse from which it came.